So thank you very much for the presentation, for the introduction, sorry. I got the request to stay here so that everything can be recorded. I will try to do my best because normally I tend to move a little bit around. I will try to think keeping my position steady. Just a few words on what we have been doing within AMAZE. We have been focused on laser metal deposition, also known as laser cladding. This is actually a technology that is traditionally used for coating and for repair operations, but it has been demonstrated during the project that it can also be used to generate parts and also to deposit 3D structures on existing components, which is one of the main benefits of this process in comparison to other additive manufacturing technologies. Also, these structures can be made of different layers, combining materials as a sandwich. It's something also that has been investigated within the project, and it's also possible to mix powders during the process online in order to produce new materials, new alloys. So as a general topic, but very early it was clear that with a view to an industrial use of this process, there are some goals to achieve. The quality of the process and the reproducibility have to be ensured. And for this, integration of specific sensors is mandatory. A little bit more in detail during the presentation on this topic. And also something important is that we need to reduce the process time. We need to optimize the manufacturing process in order to have a productivity which is suitable for the industrial use. With this goal, we have been working on two different approaches. On one side, the development of equipment and the strategies to increase the deposition rates that we can get from this technology. And the second idea is what has been called hybrid approach. Hybrid here to be understood as a combination between conventional manufacturing and additive manufacturing. With regard to the improvement of the deposition rates, at the end of the day, at TRUMPF, we are machine builders, we are laser builders, and we develop our optics. So what we have considered and tested in the project are different optic concepts with the goal to increase the laser power, the powder feeding rate, and in this way the achievable deposition rate. Normally for this technology, we use optics which create a round spot, but we wanted to explore the possibility of using square spots, and there are two possibilities to do that. It is possible to use line optics for a more or less direct creation of this square shape spots, and it is also possible to use high power scanner optics, so optics which are similar to the ones that are used for powder bed processes, but in this case with a much higher laser power. And in this case, this is what you can see on the left side of the slide. We also create kind of a square spot, but moving the laser spot in a defined trajectory. With these novel approaches, it was possible to increase the deposition rate up to over 600 cubic centimeter per hour for both Inconel 718 and aluminum silicon 10. And let's say for you to have an impression, this is a factor 5 to 10 to the deposition rate that we had at the beginning of the project. There are already some industrial projects ongoing with this type of optics, so it is not something that has been developed and put into the case. It's something that can really be used. And this was related to the approach, let's say, number 1, improvement of the deposition rate. The second approach is, as mentioned, what we call hybrid. Here, hybrid to be seen as a combination between conventional manufacturing and additive. Because, as mentioned during the introduction, a unique possibility of this technology in comparison to other additive manufacturing processes is that we can deposit on existing components. We are not forced to produce the complete part from scratch. So we can take a part and which can be forged, can be casted, and then deposit define 3D structures on this part in order to avoid let's say generating geometries which could be easily manufactured by other technologies. This was more or less the idea here. This is a blade from an industrial ventilator, and the goal here was to generate let's say the complex shape of the blade. And then on the base route, which has been conventionally produced. So it makes no sense today to produce the base of the part by additive manufacturing. It only takes time. It's an easy geometry. It can be done by using other processes. The customer here wanted to have the possibility to use a single process for the generation of different blade geometries. So this is on the blade geometry is where we can profit from additive manufacturing. So also as mentioned before, if we want to build this kind of geometry in a reproducible way by using this process, it is really necessary to integrate some sensors. Within AMAZE, what we have done in collaboration with BCT and also with the University of Birmingham has been to put a line scanner in the machine, so that we are able, after a defined number of layers, to scan the part to get the real geometry that has been deposited. And then, by means of the software of BCT, we can compare this real volume that has been generated with the nominal geometry of the part after this number of layers, and we can adapt the parameters, or some of the parameters of the process, so that in the subsequent layers, the amount of material to be deposited is as requested. So here you can see some pictures of the implementation at the University of Birmingham with the nozzle, the sensor. So a similar setup we had in our lab in Ditzingen. This is just for you to have an impression. We are dealing here with layers which have a thickness between 0.3 and 0.5 millimeters. So we really need line scanners with high accuracy in order to get the real geometry that we are depositing. Just for you here to see the scanning of a coin. But this is really the accuracy that we need to be able to get the geometry that we need to see. Again, one slide which has been provided by the University of Birmingham for you to see the differences between a process without control and a process including the this reverse engineering approach by using the line scanner. If we don't have this control, an underbuild can be observed. But if we include the control, the desired height can be reached. This is definitely something that could be learned, but also an important lesson is that this is not the end of the way. It is definitely important to be able to do something like that, but it is also important to manage to integrate additional sensors if we want to reach the goals of reproducibility and quality that an industrial use demands. So in parallel to this integration of the line scanner, we have been working with pyrometers, with near-infrared cameras for process control. We have been also integrating different camera-based systems. This was clear, it has to happen. Sorry for that. Yeah. So just for you to have a feeling, we have been integrating camera-based systems, looking through the nozzle in order to be able to position exactly, or to define exactly the position of the part or of the volume that has been generated. This information can be given to the control of the machine in order to ensure an accurate process. Do you know how can I get from here to the next? Maybe.
No, that's should have been restarted.
Okay. Ah, no, it's perfect. Oh, thank you. And also something we have been investigated is the possibility to use the laser to reduce the roughness. This means to try to avoid, in some cases, a post-processing by milling. This is just one idea. It's not fully developed, but we think it is really interesting to explore this possibility, because if we manage to remove to use the laser to remove material from the surface, to increase or to reduce the roughness of the surface, and in this way if we could avoid a mechanical milling process, for sure the post-processing could be much cleaner. We couldn't have chips. We would not have problems with wear of the tools, because no milling tool could be necessary. We could avoid vibration problems and noise problems, and for sure no cooling agents within the milling process could be necessary. So it's just something we are thinking about, and just for you to have an impression how this looks like. It's just to see a little bit the difference between the polishing that has been shown by different Hofer ILT, and this. What we are dealing with here is really material removal process, and additionally, for sure, it is possible to polish. But the main goal here is to be able to remove a layer of material by using also the laser. This video seems not to work. Sorry for that. Anyhow, thank you very much for your attention. If you have any question that I could answer, I would be very happy. to do that.
Any questions? Top? Sorry.
The last picture again.
We will try.
The system doesn't want to play at the moment. Sorry, I don't know how to. Guys, MTC, do you know how to get back to the original screen? Alt tab. Just trying to play a video.
You can.
Thank you.
The service, not only the service, but this is quite a few defects here.
Yeah, this was, let's say, only one sample that we used to try different parameters for this, let's say, material removal process. So it was just, let's say, not optimized part, and I just wanted to show that we needed several trials up to until we could find more or less appropriate parameters for this, let's say, substitution of milling. So, this is it's only been shown here. Okay.
This is strange.
This is strange. So I had a video of the process, but
I seem to have thrown. I don't know how to show.
yeah,
it. Sorry.
no problem. Yeah.
You said that you are able also to process aluminium 10 silicon. And what is the status of this development?
With regard to,
With respect to depositing aluminium 10 silicon, you showed things that were made of aluminium 10 silicon, or you were more?
there are two, let's say, basic steps with regard to aluminum. We began in a similar way, like with Incona, building walls.
Okay.
And then we got from the deposition, from this, let's say, from the point of view of the deposition rate, we got similar results. And then we have had to focus on generating structures and parts for automotive companies. So I would say with aluminum we are even a little bit more advanced than with Incona, because some automotive companies are really exploring the possibility to reinforce the parts made of aluminum, and then what we are doing is depositing aluminum 3D structures on this kind of parts. Yeah. So, but this, let's say, from the point of view of the process, is comparable to all of this. We always, I think we will always need some amount of silicon in order to avoid hot cracking. So pure aluminum, or maybe some, let's say, some aluminum alloys difficult to weld could also have here problems. But aluminum silicon 10, aluminum silicon 7 is state of the art. It's no problem.
Any other questions? Sorry, one at the top.
Oh yes.
Are you using the same laser to do the polishing?
This is a very good question. At the moment, not. So we are using a different laser for the ablation and polishing. This can be done with the same laser, but this could be now a different laser from the one that we use for the precision. It's a good point. Honestly, if this could work, it shouldn't be a big problem to integrate different lasers in the machine. For me, the main question is really to check if this approach can be a solution.
And specifically, which lasers are you using for the melting, and which laser type are you using for the ablation?
We are using, for the deposition process, we are using these lasers and diode lasers for the material removal process, we use through micro lasers and variations of margin lasers. And this is the same for the polystyrene. So picosecond and let's say a standard CD laser.
Okay, any other final questions? Okay, thank you, Antonio.